So my name's Rachel, if I don't know you, and the title of my presentation today is How Do Trees Die from Drought? And you might think this is a simple question to answer. They're obviously not getting enough water. But the drought physiology behind this is a little bit more complex with some processes that we don't fully understand. So, tree dieback due to drought is an emerging topic in Western Canada. A large part of Alberta's forested ecosystems are predicted to become much drier and more prairie-like within the next decade. And this increased risk of drought and water stress that comes with that may have a lasting impact on species distribution in the province. So, for some background, drought is known to decrease a tree's ability to conduct water. So as drought progresses, the xylem pressure becomes more negative, and this leads to an increase in loss of hydraulic conductivity. This graph, taken from a study of aspen in Colorado, illustrates how trees that were previously droughted, this black line, show an increased vulnerability to a loss of hydraulic conductivity. And this is also interpreted as an increased vulnerability to cavitation, the process of the xylem filling with air bubbles and decreasing the ability to connect water. So what is the reason for this increased vulnerability to drought, or cavitation fatigue as they call it, and what kind of mechanism is behind this? Let's see if it goes anyway. Okay, so to gain a better understanding of cavitation fatigue, I asked the question, can cavitation fatigue be linked with anatomical and or chemical changes in the xylem? For my experiment, I used two common species in Alberta, trembling aspen and balsam poplar. For part one of my data collection, for each species, I had 3 treatments: a control, a drought, and a rewatering treatment. And this data is going to be used to construct vulnerability curves like we just saw. So in order to construct a vulnerability curve, the stems must be returned first to their maximum conductivity. And so while collecting this data, I noticed, as you can see in this first box plot, that some of the droughted stems and rewatered stems did not always return to their maximum conductivity through the method that we are using. And because these trees were all from the same population, their specific conductivities, which were maximum divided by the xylem area to normalize them, they should all be from the same distribution, but they're not. So, which is interesting in itself, but for the purposes of constructing vulnerability curves, I have to remove the data that does not fall within the controlled distribution, because it's not trustworthy for knowing that it's the maximum conductivity. And so now in the new box plot, I have data that's not so normal, but this can probably something I'll have to transform later. So for part 2 of my data collection, involved scanning electron microscopy to examine pit membrane porosity in the xylem. The generally accepted explanation is that cavitation fatigue permanently damages the xylem, therefore making them more porous and leading to air seeding, which more rapidly allows the xylem to fill with air bubbles. So this box plot explores some fabricated data about mean pore diameter that I might find in aspen. So the drought and rewatered, having undergone stress, might have larger diameters, or larger maximum pore diameters, and that could be linked to this increased vulnerability to cavitation. There is a part 3 to my data collection, which hasn't happened yet, but it will be a replication of the previous drought treatments in the growth chamber, where instead of hydraulic measurements, I'll be collecting xylem sap for chemical analysis, which will then be also possibly linked to this process. So again, if we can link these structural or chemical changes to increase vulnerability to cavitation, this may help us gain a better understanding of why trees die from drought and which trees die from drought and how their distribution will be affected in the